Hmm. What am I sharing? Hey, it's right. Cool. Uh-oh, it's starting to snow. I hope we don't get that 1 or 2 or 3 inches that they were saying we might get down here. It'll melt pretty quickly, but snow has a way of making the top of the dirt where the cows walk really greasy, and that's, I mean, it's not the end of the world, but no one likes it. All right. So, just a minute. All right. Well, let's see. So diodes yesterday and transistors. Next thing we want to look at. Now diodes had 2 parts, an N type and a P type fused. And the transistors have 3 types. Well, there's only 2 things to work with, N and P. So they can be 2 P's and an N, PNP, or 2 N's and a P, NPN. 3 is, of course, 2 was di, 3 is tri, and occasionally I hear or used to hear people refer to these as triodes for the transistors, because they have 3 leads for 3 parts. Now, the dyslexic part of my mind has trouble keeping transistors straight. So every single time I have to double check everything as I go. So I'm not going to be super smooth here. There are 2 types of transistors. Bipolar is the first type, and then down a little bit later, we see the second type, which is field effect. So bipolar first. Bipolar is not anything to do with bipolar disorder, which is what they call what? Schizophrenia now? What they used to call schizophrenia. Bipolar is just 2 poles. So basically basically, we get down to the page break, it likes to jump as I scroll. So basically we have 3 parts: the base, the collector, and the emitter. Basically, the base is the center layer, and it acts like a valve to control current flowing through the whole thing. So the collector is output for a larger current, and the emitter is the current input. Now, that sounds backwards. Seems like the emitter should be the output and the collector should be the input. And this is part of why my dyslexic mind gets so confused here. because I tend to switch things, and when they're switched from what they sound like they should be, then I really get messed up. So basically, current comes in through the collector and it goes out through the emitter, and notice that's backwards of the arrow. In a lot of these schematics, maybe all of them, I'm not sure, the arrow is pointing backwards of how you think it should be. And I guess that the reason for that is because in the early days of electricity, they assumed that electricity flowed from positive to negative. I think I read that someplace. I'm not 100% on that. But anyway, so in transistors, bipolar transistors, you get two currents. How will I illustrate this? You get a small current coming in the collector and out the base. When there is a small current going in the collector and out the base, only when there's a small current coming in the collector and out the base, then you can get a large current going in the collector and out the emitter. So it turns out second, I have to see if that text is important. Nope. So it turns out that this is the current that we actually care about in these transistors. So what in the world does this do? Well, this allows us to only get a large current that we care about under the circumstances that allow a small current to flow. So we can do a variety of things with these, like use them as switches or increase small currents. Transistors are used to amplify small currents because we can, let's say, connect this to a battery so that we have a large electron source and connect this one to let's say a radio signal receiver, so that there is a small current going on there, and we can get a large current to match the small current. But the deal is, when we have a small current through the base, we can get a large current through the emitter. So they're used to amplify small signals. Here's the page break. It keeps. If we're going to amplify a small signal, the current being amplified enters through the collector, and the current entering the base. So in this case, I illustrated that not quite right. It should have been the small current going this way and the large current coming that way. Like I said, my dyslexic mind has a hard time keeping this straight. Transistors can also be used as electronic switches, just by allowing the circumstances that allow the small current to flow will then turn on the large current. Now, notice that these use a current. The bipolar transistors use a current. A small current can then result in a large current, but they have to have that small current. So that's wasteful if we are using the small current to produce large current. It's not as wasteful as it could be, but it's still wasteful. So these field effect transistors end up being a little more efficient. Now, there are two types of field effects. So, depending on how you want to identify this, you can actually come up with 4 terms. You can come up with the term, as soon as I get back up there, bipolar transistors. And then there is the field effect transistors. And then there are 2 types of field effect transistors. So, by the way, notice this. Field effect transistor, FET. So junction FETs are junction field effect transistors. So we've got the 4 terms: the bipolar transistor, the field effect transistor, the junction FETs, which are a kind of field effect transistor. And then down a little farther, we've got the down a lot farther, metal oxide semiconductor field effect transistors. So we've got actually 4 terms, 2 types, but with the 2 types and the subtypes, we actually have 4 terms. And some people get a little bit confused about 2 types and 4 terms. So basically, instead of having the gate, the base, the emitter, I said that wrong. We've got the gate, the source, and the drain, but it's kind of the same principle, except notice this. These are voltage controlled rather than current controlled. What's the advantage of that? The advantage is we don't have to waste any energy going through the small current. All we have to do is have a voltage present, and the transistor can do its job. So the gate has little or no effect on the components other than to allow it to work, which I guess you could say was an important effect. They use little or no current, but they do not handle high current or high voltage. So instead of calling them types, we call them channels: N channel, P channel, and there's the schematics. These are used to amplify small currents and switches again, as were the bipolar, but they are more efficient. They can also be used high frequency. JFETs can be used to amplify high frequency signals like radio waves and so on. And then metal oxide semiconductors are kind of the same. The gate acts like a valve to control the current leading through the transistor. It has no electrical contact, the gate that is, with the source. So in this case, a positive gate current attracts electrons, producing an N-type channel, allowing the electrons to flow. The gate voltage determines resistance. So notice this. The gate voltage determines the resistance. By determining the resistance, the gate voltage can control the, shall I say, the flow level, or in other words, these are variable current depending on the voltage. Again, we consume no power at the gate, so it's more efficient. But again, these do not handle high voltage or current, and they are very susceptible to static discharge. Man, and I've had at least 2 times, I think 3, but at least 2 times where computer devices in thunderstorms, how do I say this? Okay, you have to understand, first of all, that lightning may strike a power pole someplace, but that lightning surge is not conducted into your house. If lightning struck a power line, the power line would not conduct the electricity. If we could figure out a way that lightning could strike power lines and that power line conducted the lightning, we could utilize lightning, but the lightning charge is too strong. The lightning charge would actually vaporize the power line. So when lightning strikes close to a wire, you actually have, remember that a moving magnetic field produces electricity, and electricity produces a magnetic field, so what happens if you have a lightning strike? The electromagnetic pulse of the lightning strike produces a current pulse in nearby conductors. So you have a lightning storm and lightning strikes somewhere halfway close to where you are. That produces a pulse in the power line. It also produces pulse in phone lines. So back in the days of the early days of internet and so on, with phone-based modems, where you plugged into the phone, or in the really old days, you set the handset of the phone on some cups. But back in those days, I had 2 devices during lightning storms where the pulse in the phone line destroyed circuitry inside the device. One of them, I took the top off the computer and looked in, and you could see the top blown off, the plastic top literally blown off the integrated circuit that was damaged. So yeah, these are highly susceptible to static charges, and that's why a lot of these electronic pieces come in that special plastic that resists static charges, and that's why they're always telling you to touch the ground before you start working with these things. Well, anyway, it was getting way too hard to actually make the schematic with the nice handy little word drawing, so I just hand did it there. These are used for the same thing as other transistors, and they can be used in memory chips to store data because of the fact that they have no electrical contact with the source. Alex?
What do you mean by high current or voltage for this part?
You mean as far as an exact number?
Yeah, a general number, yeah.
Don't remember off the top of my head.
Okay.
They, I would say voltage probably over I don't know, most things are only in the 5 to 9 volt range, and I think it's probably because of this. Most of your electronic devices, if you look at the output of the transformer, it's usually in the 5 to 7 volt range. And so I expect that's the high voltage that we're talking about, not much over 5 to 7 volts.
Okay.
And as far as a current, I would have no idea on a current, but that's why I have to buy, that's the main reason I have to buy parts for the kits, is because people are not careful with the resistors that are supposed to go in. They just attach things directly, and in the 9 volt battery, boom, they can't take it and they're gone. So I keep burning up parts because people aren't careful with the resistors. So we're talking probably less than 9 volts, and I don't know what for current exactly.
Okay.
All right, that is about it. The only other thing to point out in these notes is the integrated circuits. Oh, come on, quit jumping around. And I know that you, Alex, are familiar with integrated circuits. Now these, you look at your cell phone, if you've taken apart a cell phone, which I think for you, there's a good chance you have. Some of these ICs are like, some of the big ones are a 1/4 inch square, and the small ones are some tiny, tiny fraction of an inch. So when we say microchips, we are really talking micro these days. All right, that's the end of the notes. There's not much. Hopefully we can get the kits put together and you can get going on kits next week. I'm not exactly sure how that's going to work. So unless you have something else, Alex, I'm going to let you go. All right, then. Have a good day.